Hello, friends. Today we're going to be talking about cardinality, a way to talk about the quote-unquote size of sets. It's important to keep in mind that cardinality is not the be-all and end-all definition of size for sets. There are many different, yet equally important notions of size. As an example, let's consider the real numbers between 0 and 1. On one hand, we can think of the size of the set as being infinite, since there are infinitely many points in this set. On the other hand, we can think of the set as being a line segment with length 1. Each of these notions of size is correct in its own way, and it does us no favors to declare one of these as the definitive definition of size, ignoring the other notion and the understanding that it might offer us. Now, what is cardinality and what notion of size does it capture for sets? Two sets have the same cardinality, or quote-unquote size, if there is some way that we can pair up the elements one to one. Or in other words, there is some bijection from A to B. The way that I like to think about this is I imagine myself walking into a shoe store. As soon as I walk in, I know that there are going to be as many left shoes as there are right shoes, because I know there's a way to pair up the shoes together. Or in other words, there's a bijection from the set of left shoes to the set of right shoes. Also, another way to describe two sets, A and B, that have the same cardinality is to say that they are equinumerous. We denote two sets being equinumerous by writing a tilde between them. It actually turns out that this is an equivalence relation, which means that we can group sets together based on whether or not they have the same cardinality. Every set is equinumerous with itself because the identity map that sends every element to itself is a bijection. So every set has the same size as a copy of itself. Cardinality is also symmetric, because for every bijection from A to B, we can invert that function to get an inverse bijection from B to A. So if a set A is the same size as set B, then it makes sense that B is the same size as set A. Finally, suppose that a set A is equinumerous with set B, and set B is equinumerous with another set C. We can compose the bijections between these sets to get another bijection between A and C, showing that these sets are also equinumerous with each other. So if A and B are the same size, and B and C are the same size, then it follows that A and C also have to be of the same size. If we're dealing with finite sets A and B, then there's only a bijection between them if they have the same number of elements. However, for infinite sets A and B, it becomes much harder to tell if these sets are equinumerous or not. Finally, one last definition. If a set A is equinumerous with the natural numbers or is finite, then we say that set A is countable, meaning that there is some way of counting every element of A. If A is infinite, then this counting process will never terminate. However, every element of A will be counted after some finite amount of time, although said amount of time might be extremely large. Now let's look at some examples of countable sets. Of course, the natural numbers are countable, following from the reflexive property. What's more surprising is that the natural numbers have the same cardinality if we remove the element 1. We can express this set as the natural numbers plus 1, because if we add 1 to every natural number, then we end up with every natural number except for 1. This function of adding 1 to every natural number is actually a bijection from the natural numbers to the natural numbers plus 1. For finite sets, removing a single element would definitely change the size of the set. But for infinite sets, removing a single element isn't significant enough to affect the cardinality. Infinity minus 1 is still infinity. What happens if we try cutting out a larger chunk of the natural numbers, say half of them? Well, it turns out that the cardinality is still not affected. We use the symbols 2 times the natural numbers to denote all the even numbers. Because if we multiply every natural number by 2, we end up with all of the even numbers. Even though the set of even numbers is missing half of the elements of the original natural numbers, the function mapping between them, 2 times n, is a bijection, showing that the natural numbers and the even numbers have the same cardinality. Infinity divided by 2 is still infinity. Using this idea, we can figure out that the natural numbers and the integers have the same size under cardinality. We can construct a bijection between them that sends all of the odd natural numbers to all of the non-negative integers, and all of the even natural numbers are sent to the negative integers. For the previous examples, I didn't explicitly show that the functions were bijections, leaving the details of the proof to you, the viewer, as an exercise. But since this latest function is more complicated than the previous ones, I'll go through all of the steps of proving that it's a bijection. First, we will show that this function is injective. Suppose f of n1 equals f of n2. If n1 and n2 are both odd, then they have to be equal. If n1 and n2 are both even, then they also have to be equal. If one of n1 and n2 is odd and the other is even, then we see that we must have n1 plus n2 equals 1. But this contradicts the fact that n1 and n2 are natural numbers, so their sum has to be at least 2. Thus, if f of n1 equals f of n2, then either n1 and n2 are both even or both odd, in which case it follows that n1 equals n2. So this function is injective. Now we will show that this function is surjective. Let z be some arbitrary integer. If z is non-negative, then 2z plus 1 is an odd natural number that gets mapped to z by f. If z is negative, on the other hand, then negative 2z is an even natural number that gets mapped to z by f. So we see that f is surjective, and since it is also injective, f is bijective. And we conclude that the natural numbers and the integers have the same cardinality. We will now prove an important theorem about countable sets. Let A be a countable set, then every subset of A is countable. Consider a subset B of A. If B is finite, then it is countable, so we're done. On the other hand, if B is infinite, then since A contains B, A must also be infinite. Then since A is countable, there must be some bijection f between A and the natural numbers. We can actually use this bijection f to order the elements of B, simultaneously finding a way to count the elements of B, and also finding a bijection between B and the natural numbers. We can choose the first element of B, B1, as being the element of B that gets mapped to the smallest natural number in the image of B. Here, min f of B denotes the smallest natural number in the image of B. Argmin f of B denotes the argument of f, or the element of B, that gets mapped to this minimum. We can pick the next element B2 as being the element of B that gets mapped to the second smallest natural number in the image of B. We can continue this process, indexing all of the elements of capital B, and then we obtain a one-to-one correspondence between the natural numbers and the elements of B based on their indices, a bijection, thus showing that an arbitrary subset B of A is countable. We will now explore some conditions under which a set is countable. The following statements are equivalent. 1. A set A is countable. 2. There is an injection from A to the natural numbers. And 3. There is a surjection from the natural numbers to A. In order to show that these three conditions are equivalent, we will need to prove 6 statements total. We need to show that if 1, then 2 follows, and if 2, then 1 follows, and if 2, then 3 follows, and so on. Thankfully, there's a trick that allows us to only have to prove 3 of these statements, and the remaining 3 fall out as consequences. We only have to prove statements so that they form a circle like this. Any of the 3 remaining statements can be obtained by just going around the circle. We will now begin the proof. We need to show that if 1, then 2 follows. Suppose first that A is finite, in which case we can express A as a sequence of elements labeled from 1 to some natural number n. There is an obvious injection from A to the natural numbers that sends each element to its index. Now, let's consider the case that A is infinite. Since A is countable, there is a bijection from A to n, which by definition is also an injection, so we're done. Now we need to show that if 2, then 3 follows. Let f be an injection from A to the natural numbers. F becomes a bijection if we restrict the codomain to the image of A. Furthermore, the inverse relation f inverse becomes a bijective function if we restrict the domain of f inverse to the image of A. We now have a surjection from a subset of the natural numbers to A. To obtain a surjection defined on all the natural numbers, we just need a place to send all the natural numbers that aren't in the image of A, which can be some arbitrary element of A that will denote A0. Finally, we need to show that if 3, then statement 1 follows. Let f be a surjection from the natural numbers to A. We can partition the natural numbers according to which element of A each one is mapped to. If we send each A to the minimum number in the associated equivalence class, then we can obtain a bijection from A onto a subset of the natural numbers. We know from the previous problem that every subset of a countable set is itself countable. If n of A is finite, then A must also be finite, hence countable. If n of A is infinite, then since it's countable, there is a bijection between n of A and the natural numbers. We can compose this bijection with the previous one to obtain a bijection from A to the natural numbers, which shows that A is countable. In the next problem, we will prove a powerful result about countable sets. Consider a countable family of countable sets. Then the union of all those sets is itself a countable set. Also, when we say that a family of sets is countable, we mean that we can index that family according to a countable set, which in this case is I. For now, let's consider the case where every single one of the sets AI is finite. In this case, there are bijections from subsets of the natural numbers to each AI. Here, we surround a set in absolute value symbols to indicate the total number of elements within that set. To show that the union of the family is countable, it suffices using the results of the previous problem to construct a surjection from the natural numbers onto the union. We can obtain this surjection by applying the maps fi to different intervals of the natural numbers. If there are only finitely many maps fi, we can send the remaining elements of the natural numbers to some common element in A1, for example. Also note that we may need to modify values before we send them off to the corresponding fi map. For example, if we wanted to apply the surjection to the absolute value of A1 plus 1, we would first need to subtract the absolute value of A1 before passing it on to F2. Here's another way to think about this. We essentially need to find a way to count all of the elements in A1, A2, and so on. It's actually pretty easy to do so. We just go left to right, top to bottom. This counting process works because each AI is finite and has an end, so we will reach every element eventually after some finite amount of time. Also, this counting process shown here is essentially the same thing as the surjection we constructed. Now, we consider the case that each AI may or may not be finite. The previous counting process of going left to right won't work here, because if A1 is infinite, then we're never going to finish counting A1, and we're never going to reach the elements in the other sets. The key here is to rethink the way that we view this union. Notice that even though each AI may or may not be finite, each diagonal of the union will always be finite. This means that we can view the overall union as the union of the diagonals, or in other words, as the union of finite sets. There are countably many diagonals, and we know that the countable union of finite sets is countable. Thus, we conclude that the overall union is countable. The actual process by which we count this set looks like this, where we basically zigzag through the whole union, counting each element in each diagonal. A direct consequence of this theorem is that if A and B are countable sets, then their Cartesian product will also be countable. Why? Because we can express the Cartesian product as a union of sets. Each set is countable because B is countable, and there are countably many sets because A is countable. Another consequence of this theorem is that the set of rational numbers is also a countable set. This is because we can view each fraction as an ordered pair of the numerator and the denominator. For example, we could view 2/3 as the ordered pair 2, 3. As for the rational numbers that are also integers, we can view them as fractions with a denominator of 1. So for example, we could view -5 as being the ordered pair -5, 1. One slight technical hiccup with this approach is that there are multiple ways to express a rational number with ordered pairs. For example, we could choose to represent 2/3 as either being 2, 3, 4, 6, 6, 9, and so on. We can avoid this by reducing every fraction before converting it into an ordered pair, so that every rational number corresponds to a unique ordered pair. This means that there's a one-to-one correspondence between the rational numbers and a subset of the integers cross the natural numbers. So in a sense, we can view the rational numbers as being a subset of this set. The integers and the natural numbers are both countable, so their Cartesian product is also countable. Every subset of a countable set is countable, So we conclude that the rational numbers are countable. At this point, all we've seen are sets that are countable. We are now going to take a look at a set that is not countable. The real numbers are not a countable set. When we say that a set is uncountable, this means that any way we try to count it will unavoidably miss some element of the set. So for any countable list of real numbers, we will always be able to find some real number that is not in that list. Notice that there's a one-to-one correspondence between a countable list of real numbers and the digits of a real number between 0 and 1. This is because every real number has countably many digits after the decimal point. It only takes one differing digit for two real numbers to be unequal. So to find a real number that's on this list, we're going to construct a real number between 0 and 1, where each digit after the decimal point is going to have a specific job. Each digit will ensure that the real number r is different from a specific real number in the list. For example, if r1 had a digit of 4 in the tenths place, then we would pick the tenths place digit of r as being any digit other than 4, like 5 for example. If r2 had a 6, for example, in the hundredths place, then we would pick the digit of the hundredths place of r as being any digit besides 6, like 3 for example. Continuing to pick digits this way, we arrive at a real number r, which, by construction, is different from any of the real numbers in the countable list. Thus, we conclude that the real numbers are not countable. This theorem also implies that the set of irrationals is not a countable set, because if it was, then we could express the real numbers as a countable union of countable sets, which would imply that the real numbers are countable, a contradiction. In this video, we managed to learn the basics of cardinality, and also learn some important theorems surrounding countable sets. In the next video, we're going to continue to learn the basics of cardinality. Most importantly, we're going to learn the very powerful Schroeder-Bernstein theorem. But until then, thanks for watching. Remember to like and subscribe as it really helps out the channel. Also, make sure you're drinking enough water every day. Bye!